So in this lecture, we're going to talk about a new reaction called the Aldol condensation reaction. So there's, I guess all of these words are familiar with you. You're familiar with, are familiar to you. The aldol kind of reminds us of the aldol reaction from the previous lecture, and condensation means we will have a small molecule byproduct. And our favorite condensation reactions are those that release water. And this is indeed another reaction that releases water from the starting materials, I guess. Okay, so what we're doing in this reaction is we are converting the aldol product, which I started last time by telling you that the aldol product was an aldehyde alcohol, but then I turned to saying, let's instead think about that as a beta hydroxycarbonyl. Okay. So we are going to convert the aldol product into an alpha beta unsaturated carbonyl. So here's the general reaction. We are going to take our carbonyl that has a beta hydroxy group. You can have R's at the various positions, whatever we need. Okay. And we are going to eliminate water from the reaction to make an alkene. So these two atoms are going to be lost. So this is different from the aldol reaction. This is the aldol condensation reaction, I guess. Okay. So these two are going to be lost to give rise to water. Now the outcome in terms of our carbon atoms is that we're going to see this product being formed. Okay. So our site of unsaturation has been added to the molecule, hence the term unsaturated carbonyl. Okay, we have a carbonyl present, but we have a site of unsaturation nearby that carbonyl. Now, additionally, what I want to point out is that unsaturation unit extends from the alpha position to the beta position. Okay, alpha to beta unsaturation. Okay, so alpha beta unsaturated carbonyls have a CC double bond between the alpha and beta carbons. Okay? They result, so they have this, they result when an aldol product loses water. And what we get is HOH, where one of the H's was once an alpha hydrogen. Hopefully you can see that from my highlighting up here. We have our alpha hydrogen, so that's inherently acidic. And the other, the OH, was the beta OH. Okay, so those things are lost as a result of this reaction. Okay, so let's go ahead and draw some mechanisms for it so we can try to understand it. I've tried to give you some hints. Now, here's kind of the issue with the aldol reaction, or the aldol condensation reaction, is the condensation can happen with heat, base, or acid. Heat, base, or acid. Okay, let's look at how these things work. When it's acid or base, it turns out that it can be catalytic in the presence of base, and it's often catalytic with acid. And heat, I mean, catalytic heat, let's not worry about that today. Okay. All right, so we have heat, base, acid. These are the three conditions. So does that mean we have three mechanisms to consider? Yeah, sort of. Okay. Let's do the acid mechanism first. And this really is the one that occurs with heat. So typically when you try to force this to occur with heat, you tend to, I mean, you can do it with base or acid, but you generally, I want you to think about, let's just do acid and base for this class, just acid and base conditions. The heat will get wrapped up in the acid conditions. Okay. So with the acid mechanism, what we're going to start with again is the aldol product. I'm just going to put one R group. I'm not going to worry about the alpha position. Okay, so now we're going to add H+. Now H+ always reacts first because it's a subatomic particle floating around. Okay, so we're going to let that react on the OH because we need to lose H2O. And you can have a little hydrogen bonding interaction there if you want to understand why we get that stabilizing, why we go to that particular oxygen. But at this point, once we add the H+, what we can do is lose the alpha H+. It's already kind of acidic, right? Because it's next to a carbonyl. We can lose that H+ and then push off the H2O to give rise to the product. Okay, so not so bad. We put the H on the OH, it's already a good leaving group. The H at the alpha position that needs to be lost anyway is already acidic, so that's going to fall off. And what we get is H2O plus our product plus the H+ that just fell off. And this is another example of an acid catalyzed process where the H+ we put into the reaction isn't the H+ we get out, but it's still regenerated over the course of the reaction. So IUPAC says still catalytic process. Okay. So that's our acid mechanism. Now our base mechanism involves what's called the E1CB reaction. The E1CB reaction. So if we see E1, what we want to think about is elimination with an intermediate. Elimination with an intermediate. Another way of saying this is in the rate determining step, there's only one species involved. In this case, it's our carbonyl containing thing. But I just, when you see E2 or SN2, think no intermediates. Everything's concerted. With E1, SN1, that sort of thing, we have some sort of intermediate. Now, in all of the E1 and SN1 processes we've looked at, I said, okay, automatically think carbocation. Think carbocation. Okay, now with E1CB, that little CB qualifier, we're actually going to have an elimination reaction with a carbanion. Now, does the CB stand for carbanion? It can if you need it to, because we're going to have a negative charge. I think it's supposed to be carbonyl, but I don't want to get into that. The carbonyl is kind of the reason why this works. So if you wanted to think carbanion, if you see that CB, go for it. Okay, what does this reaction look like? Well, it's really not that big a deal. What we're doing is we are reacting our aldol product with some base. I should just leave it as a generic base. I don't want to. Okay, yeah, I'm gonna put hydroxide on here. Okay, I did it. It's done. Okay, so the hydroxide could engage the alpha position of our carbonyl to generate an enolate. So we could dump that negative charge on the alpha position, or we could draw the enolate being stabilized by the oxygen. Either one is fine. But at this point, we have an intermediate, and the negative charge is going to come over and push off the OH to generate this. My sense is this is probably what happened in the lab where we made dibenzyl acetone. Okay, so that's a distinct mechanism from the acid catalyzed reaction, where we have some base generating an anion, which will sort of force the ejection of the OH minus. So in this case, it's catalytic because you generate some OH minus and it can just kind of keep propagating over and over again. Okay, I don't want to go through that much more than I need to. Okay. Instead, I want to talk about some other aspects of the aldol condensation, which are when does the aldol condensation occur? Okay, so for you, it's when base and heat or acid and heat are added to an aldol reaction. Okay, so when these things are added to an aldol reaction, so let's say we take this, our previous aldol reaction. Okay. What we did was we had step 1, we added base, and step 2, we added H plus workup. And we had a slight excess, a small excess, not an excessive excess of this being added, and we did an aldol reaction. Okay, so this is an aldol reaction, not to be confused with the aldol condensation that eliminates water to make a carbon-carbon double bond. So that would be a normal aldol reaction. If instead I said, let's take these two things, and then we'll do, in step 1, we add base. In step 2, we add H plus and excessive heat. If we add excessive heat, then we're going to draw the exact same framework, but we're going to have a double bond extending from the alpha and beta position. This is going to be our alpha beta unsaturation unit. Okay, so that's what you need to know. Now, in reality, when does it occur? It kind of depends. It depends on how stable the resulting alkene is. If you notice, the alkene in the alpha beta unsaturated system is in conjugation with the carbonyl. That's great. That's a good deal for the alkene, right? It's in conjugation, so we get that conjugation stability. If we tried to hydrogenate that alkene, we wouldn't release as much energy as we would otherwise. You know, CF, the aromaticity section of the class. Okay, so that helps, but that's just a general phenomenon of all aldol products. There's some aldol products where they're on the opposite side of the carbonyl. On both sides, there's benzene rings present. Okay, think about the reaction that we did for lab, the dibenzyl acetone. There were benzene rings on either side, and so if an alkene formed, it would not only be in conjugation with the carbonyl, but it would be in conjugation with the benzene ring. So all of these things will stabilize the resulting alkenes and further make it easier to lose water. So you don't need as much heat and as much acid. And maybe the heat that's required is the heat that's provided by room temperature. And you are not even able to get the beta hydroxycarbonyl because instead it just eliminates to make the alpha beta unsaturated carbonyl, that alkene. Okay, so anyway, what we've done today is taken the reaction from last time, the aldol reaction, and pushed it forward to the aldol condensation reaction, but we've also introduced a new functional group, the alpha beta unsaturated carbonyl. So next time we're going to be looking at the chemistry of alpha beta unsaturated carbonyl. So I look forward to seeing you then.